3.5, we're going to be taking a look at trigonometric equations. These are not verifying identities, all right? The goal is not to make the left-hand side look like the right-hand side. The goal is to solve for x, okay? Solving for x. In some ways, this is far more like algebra than anything we have done in this chapter so far. But because we did 4 sections of all the other stuff, it feels really different because it doesn't look like what we've been doing. So some basic strategies first for solving trig equations. So the first thing you probably need to do is to decide if it's linear or quadratic. So if you remember those terms, great. If not, let me remind you. Linear just means that it is something, I'll give you an example of a linear equation. Linear would look like in algebra y equal mx plus b, right? And quadratic would look like y equals ax squared plus bx plus c. What's the difference in these? I know there's a bunch of letters difference, but there's something that's important. Yeah, there's a parabola or a line, and the parabola is being created because there's an x squared, right? So the primary difference in these equations is, do I have an x squared? Because if I have squared pieces, I'm going to operate a little differently than when I don't. So that's why I'm going to need to identify what kind of equation am I working with. The next thing to notice is if there's only one trig function present, we're going to do something slightly different. So if there's one trig function present, we're going to solve the equation for the function. So like if there's a sine of theta in there and that's the only trig function, then the goal is to get sine of theta on the side by itself and everything else on the other side. Just like when we're solving linear equations back in algebra, the goal is to get y on the side by itself and everything else on the other side, right? If you're trying to solve for y or whatever the letter was, or x. If there's more than one trig function present, then you need to rearrange it so that everything is set equal to 0. So if you have a sine squared and a sine, or if you have a sine and a cosine, right? You want everything on one side and you want 0 on the other side. That's very different than what step 2 said, right? So it depends on which one we're working with. And step 4 says, and then it says let me finish 3. Then try to factor and set each factor equal to 0 and solve. And then step 4 says, try using identities to change the form of the equation, okay? So we will see that used frequently. So if you don't have them out already, go ahead and get out your sheet that you're going to be able to use on your test that has all of your trig identities, starting with sum and difference. So it looks like this. I handed this out a little while back, a white sheet. You'll get this on the test, a brand new clean version of it. Okay, it'll look just like this one, but it'll actually be on a colored sheet of paper. And so have these present with you as we're working through these. We are going to take a look at these from time to time and be able to utilize them. All right? So obviously we're going to start with something that's super straightforward and simple, and then they're going to get more complicated as we go in this section. Make sense? Yeah, okay. So let's take a look at this one. First, this one's directions simply say to use substitution to determine if the value is a solution. We're not asked to find if it's a solution. We're just asked to decide if it works. So what does that mean? Well, it means taking this x value and putting it in here and checking to see if it works. So we're going to put the pi over 3 in for x. Okay. And then we're going to think unit circle, right? So our goal is to see, right, this is like a question mark. Does it in fact equal square root of 3? I don't know. So we're going to use our unit circle. So what quadrant are we in if we're at pi over 3? 1. How close are we to the x or y axis? Which one are we closer to? Yeah, we're closer to y. So we're up here if we're at pi over 3. Okay. What's our ordered pair at pi over 3? 1/2 and square root of 3 over 2. Everybody good so far? If this had just said sine or cosine, you'd just be done and you'd know whether or not it worked, okay? And so how do we decide for tangent? Tangent is sine over cosine or y over x. So the y value is square root 3 over 2 and my x value is 1/2. Okay, how do I simplify that? Yeah, you can multiply by the reciprocal or you can multiply by the little denominator of 2, either way. So I heard this one first, so we're going to multiply by the reciprocal. So what happens when I multiply square root of 3 over 2 by 2 over 1? Yep. And eventually the 2's will cancel either in this step or in a simplified step, and we get square root of 3. we verified that this works. This is sort of a bridging problem because we are verifying something just like we were in all of the last sections with our identities, right? But we're verifying specifically a solution this time, not an identity. Okay, we're verifying a solution. So what if this had said pi over 6? Well, if it had said pi over 6, it wouldn't have worked. It wouldn't have equaled square root of 3 at the end, and the answer would be no. And so the question says, determine if it's a solution. The answer is that it is. So this is a solution. If we had had a different angle measure that was given to us to try out, it might have been not a solution, and we would say it's not a solution. All right? Okay, so let's actually move then into the ones where we have to find the solutions, which is the majority of what's in this section. Okay, so it says to find all the solutions of the equation. So let's just kind of take a look back up at our basic strategies. The first thing said to decide if the equation is linear or quadratic. Is this linear or quadratic? It's linear. There's no powers of 2, right? If there's no powers of 2, it's linear. Okay, so it's linear. Everybody good with that? Okay, cool. So if it's linear, we're going to keep moving down, just kind of keep that in mind. Number 2 says, if there's only one trig function present, solve the equation for the function. That's what we've got here, right? There's only one trig function present. It's sine. Everybody good so far? Okay, so what means we want to have sine of the angle, in this case it's x, all by itself on one side. We'll leave it on the left. And then we want to move everything else to the right. So what do we shift first from an algebra standpoint? The 3, you bet. So we're going to subtract our 3 first. So that's going to give me 2 sine of x equals 1. Then what? Then we're going to divide by 2. So now I have the sine of x is equal to 1/2. Okay, so everybody good so far? Let me pause just a second. Okay, so what did you have in mind next? Yeah. Now, it sounds really straightforward, but it's a little bit more complicated of a process. So let's take a look at our unit circle. We need to first identify which quadrants sine is positive. 1 and 2. Okay, so there's potentially 2 solutions, one of them in quadrant 1 and one of them in quadrant 2. Where do you get angles, or at what angles do you get sine values that are 1/2? Good. So they are the ones that are closest to the x-axis. So remember all of our work of our unit circle, right? We're using it again here. So this one is pi over 6. And this one over here is at 5 pi over 6. How's that all the solutions? So way back in chapter 1, we talked about the ability of taking any particular angle measure we're at. Let's just talk about pi over 6 over here on the right-hand side. So I'm at pi over 6. And if I went all the way around this circle, 2 pi, I'd be back at pi over 6, right? But because I've gone all the way around and a little bit more, I haven't just traveled, if you will, pi over 6. I've traveled pi over 6 plus 2 pi, right? So you see this happen all the time when you are looking at sports where people do turns, whether it's swimming or like diving. Diving is a better, what I meant to say, diving. So if people do dives, you see it in gymnastics when people do spins on like the beam or along a bar. You see it in extreme sports too, like bicycles, like what's the word I'm looking for? You know, like the bikers, right? Like the bikers when they do the spins on the cycles, yeah. And skateboards, right? Same thing. So they're doing this spin, right? So like if I'm looking at you and I go all the way around, that's a 360. That's not 0, right? If I do it enough, I get dizzy. So the problem is that this question is not super simple. There are infinitely many locations where sine is equal to 1/2. But we can express them in a concise form, and here's how. So we first identified 2 locations. We identified pi over 6, and we identified 5 pi over 6. And sometimes your directions will say, I only want the solutions between 0 and 2 pi. And if it said that, we would be done. This problem doesn't say that. It says all, doesn't it? All solutions. So here's what we do. We say, okay, but I could add 2 pi to this, and it would work. And I could add 2 pi to this as it would work as well. Then I could also add another 2 pi, and another 2 pi, and another 2 pi. And technically I could also subtract 2 pi, right? I could go backwards around the circle and I could end up there. So here's how we represent this generically. We put a k, or sometimes I'll use an n. And this k or this n is, that's not the word I wanted, an integer. Any integer value. So it could be 36. I would add 2 pi 36 times, and it would still be a solution, right? It could be negative 12. I could subtract 2 pi 12 times, and it would be another solution. But by putting that k on there, I'm able to show that I can keep doing this repetitively over and over again. So this is the form that it will look like when we see a question like this. And we have to identify that whatever letter we're using, and k and n are the usual ones that are used, is an integer. Okay, so let's try one now that doesn't have that caveat. It actually says on the interval 0 to 2 pi, which means it's easier. We don't have to do any of the extra stuff we were doing there at the end. Okay, so first, is it linear or quadratic? It's still linear. Do I have still one trig function? Yes, I do. It's not a very pretty trig function, right? Cotangent's not as friendly as, say, tangent, so you might want to change it if you wish into tangent. You can deal with it with cotangent as well. Or you can change it into something more familiar with sines and cosines, which is kind of nice when we're dealing with tangents and stuff. So I'm going to choose that way on this particular one, not because it's the only option, but because we haven't seen it done, okay? So what is cotangent in terms of sines and cosines? Very good. Cosine over sine. Now, I'd like for you to notice that this is a triple angle, right? There's a 3 theta in here. We're going to have to deal with that in a slightly different way, so be prepared. We're not going to actually be able to be finished when we find out that angle equals something here in a moment, but that's going to be part of it. This has square root of 3, so square root of 3 is the same as square root of 3 over 1, which I'm going to just write it like that for the moment to remind us. So I want you to think about on a unit circle, because these are going to be values typically that are going to be unit circle values. Where do you get square root of 3's that are connected to cosine? So at pi over 6, yes. And then there would be the other pi over 6 values in the other quadrants. I should have stopped and said which quadrant we were in first. So which quadrant are we in? If we have a cotangent value that is positive. We always get to be in 1 if we're positive, right? So, oops. 1, and is it 4 for cotangent? I don't think it's 4. I think it's 3. And another way you can think about it, if you're struggling to remember, because we, again, usually think about tangents and tangent instead of cotangent, is that I need my sine and my cosine signs to match, right? They need to either be both positive, that's quadrant 1, or need to be both negative, and that's quadrant 3. So it's in quadrants 1 and 3. Okay, so Emily, you had said that we're over here at pi over 6, which is correct. What about if we're in quadrant 3? What is the over 6 value? It's 7. Yep. So this one over here is 7 pi over 6. It's probably worth noting that these are exactly pi apart. So that's another way to express this. We could actually think about it from that perspective. I want to write down a few more values going around the circle, like multiple times, specifically. So this angle that I'm giving, which is 3x, I've got pi over 6, which is one option, and I've got 7 pi over 6. Notice what I'm going to have to do. I'm going to have to divide by 3 to find x, right? Does that make sense? What that means in terms of my unit circle is while my answer is going to be between 0 and 2 pi, that's true. Because I've got 3x that I'm going to divide by here in a moment, I need to go around the circle 3 times to get all the values, because when I divide by 3, it's going to divide all those numbers by 3. And they will be within 1 unit circle. Okay, so just take a look with me. If I were to take this one and now go all the way around to here, how far have I gone? What's the next pi value after 7 pi? It would be 2 pi added to the pi over 6. So what is pi over 6 plus 2 pi? we're asking the question, what is 1/6 plus 2? It's 13 pi over 6. Your calculator will help you if you don't want to have to think too hard about the fractions. It's 13 over 6. What if I go another pi over to here? Or equivalently, what did I have to add to 1/6 in terms of sixths? 12, right? So if I add 12 to the 7, what do I get? Okay, 19 it is. Right? All I'm doing is I'm adding 12 here, 12/6. I'm adding 12/6. But I need to do one more set. We're going to add 12 over 6 one more time. So what is 12 over 6 plus the 13 over 6? 25 pi over 6. And what happens if I add 12 again? It's 37 pi over 6. It's also worth noting on this one particularly, like we had said, if you take a look at the tops, we're just adding 6 every time. Do you see that? And the reason we're adding 6 is because 6 over 6 is 1. Okay. How do I know I can stop? Well, I actually know I can stop because there's 3 unit circles worth here. And I've got a 3 here. That's how I know. So if this had just said 2x, I would only had to have 2 unit circle worths of this. If it said 4x, I'd have to do it 4 times.
If it said all?
If it says all, we're going to do it like we did over here. Okay? And kind of, yeah. I mean, there's a simpler way of doing this particular one in terms of conciseness. Oops, sorry. And then I need to divide by 3, right? So I need to divide each of these by 3. But what happens when I divide by 3 for fractions? Multiplies the denominator by 3, right? So this is an 18 on all these fractions denominators. If any of them will simplify, we will do so. I don't think any of them are simplifying yet. So I don't think we're going to have any of that. And if you're not sure, like, did I give too many of them or did I not give enough or whatever, like give too many would be a good question at this point. Take your calculator real quick. What is 37 over 18? It's going to give you an ugly decimal. That's okay with me. What's 37 over 18? It's what? Try again. No, not with the pi. I'm sorry. I probably said it wrong. Just the 37 over the 18 part. I don't want to deal with the pi. I want to look at the other part of it. 2.05. I think our 37 on the end was the wrong number, wasn't it? It should have been 37. Let's go back and catch that. That's an error. Let's see, 25 plus 6. I think it should have been a 31. Is that right? I think we probably added 12 to the 25 instead of adding 12 to the 19 when I did that. That was probably my fault. How about 31 over 18 then? Because that's the one I want it to be. 1.72. Okay. What I wanted to show you, and it caught us in error, so that's good, is that this number at the end has to be smaller. I mean, the number that's multiplied by pi has to be smaller than 2. If it's not, I'm not within 2 pi rotation, right? I'm not between 0 and 2 pi. So I get 6 answers instead of just 2 because it's a triple angle. I have 3 times as many answers. And we will stop there for today.